This video is an overview of an ESP32s3 project that I recently posted to GitHub. Hopefully, this better explains what's in the project and why you might want to look at it. So, to start, if you follow the channel, you know I've built several versions of CW decoders, supposedly each a bit better than its predecessor. Arguably, better is a relative term here, and admittedly the trend has been with increasing material costs, but like to think the features added offset the cost. The latest example being the WaveShare ESP32s3 version with its 7-inch display and Bluetooth BLE keyboard support. After working on this project for a while, I felt to improve it further, and I'm talking about the decoder here, I needed to refocus on the tone detection process and what might be done external to the receiver to improve separating the tone from the noise. And to better understand what I was doing or the effect that a given noise reduction strategy had, it would be beneficial to have a test bed that had a sound in, sound out architecture. Now, because I had a spare WaveShare board from the previous project, it was the natural choice for the hardware side of this exercise. However, the one feature this board appears to lack is a sound out connection. A little Googling returned that the expressive library set supported configuring the USB connection as an audio sound card, also known as UAC. For my initial needs, that was good enough. As I reasoned with that, I could send the sound directly to my computer where I could record it and or reroute it to a speaker and decoder to evaluate the effectiveness of any DSP processing that I added to the data stream via the ESP32. So that's the first thing this project brings to the table. The basic code needed to take an analog signal, apply it to the ESP32's ADC, and pass it out through the USB interface to your computer. Now, having said that, let me set some ground rules about what you'll see in this video, or maybe more importantly, what you won't. It's not a line-by-line review of code. For those who are looking for that, I apologize and offer this as an alternative. The project's IDE is VS Code and Platform IO. Today, VS Code supports the AI tool Copilot. I found you can highlight or select a section of code and ask Copilot to explain it. Honestly, it does a better job than I can. What I find impressive is it doesn't just read you back the highlighted code like this is a for loop with two if statements, but instead explains how the selected code works inside the project, including the libraries linked to the project. Now, the next thing to know about this project is all streaming is done as monophonic audio with a 16 kHz sample rate and is band limited to approximately 3 kHz. In other words, telephone quality audio. And last, to be clear, the project was built around the ESP32s3. If I say ESP32, I really mean the S3 version. Now, back to the first audio in-out interface. I don't want to tell you how long it took me to get this piece of the project to work. But if you're a newbie like me and you want to create your own UAC interface, seeing how this project is organized and how the libraries are invoked could save a lot of time. For what it's worth, this approach is just one way to get things going. If you have a better way, I hope you'll share it. In spite of Expressive's online documentation and examples, I found it challenging to figure out how to create a working, real-world USB audio interface. For example, one major stumbling block for me was managing the USB callback for more sound data. It's supposed to be an app-level callback, and as such, I assumed it would fire just as the USB's FIFO buffer was about to run dry, and or the request count argument would represent the number of bytes needed to replenish the buffer. Not true. Turns out it fires as fast as it can loop through the USB mic task found in expressive USB_device_uac.c file and asks for the full buffer count every time, regardless of what remains to be sent. So if fed as fast as it asks for it, you'll overwrite data that has yet to be sent across the USB interface, and the audio heard on the computer side will be garbage. So in the main CPP file, in the function uac_device_input_cb, you'll see code that retards the callback's return until just the instant the buffer would run dry based on lapsed time since the last update. A whole video could be done on just this aspect of the project, and as said earlier, anyone knowing a better approach, please leave a link to where your example code can be found. But for now, let's move on and look at the project's second audio output interface. Expressive I2S library supports PDM, pulse density modulation. So, while the Waveshare board has no analog output per se, we can pass the PDM data out via UART2's receive pin, connect it to a simple RC low-pass filter, and then AC couple that to construct an analog output signal. The output is a bit low, but quite usable, and given the hardware simplicity, is now my preferred way to pass processed audio onto other devices, i.e. the speaker and decoder. 2 points here. First, the project supports using one or the other output method, but not both at the same time. And the second is, you select the desired output mode from the display, but have to then restart or reset the board before your selection takes effect. And remember, if you're using the PDM method, UART2, there's a switch on the back of the board that directs which connector UART2 is connected to. Okay, that covers how to get sound out of the board. Now, let's look at the 4 filter options available via the display button. First, of course, there's a straight-through mode. This actually applies a simple 8 kHz low-pass filter to the ADC data, but otherwise is not modified. Second is a one-stage IIR filter centered at 750 Hz and is roughly 300 Hz wide. And for CW work, makes a nice comparison to the straight-through mode. Next is something called NS-Net2. This one warrants some explanation. For CW work, it's worthless, but for SSB reception works quite well. It's part of Express's voice recognition library or component set. If you Google NS-Net2, it will tell you it's, and I'm quoting here, a deep learning model primarily used for deep noise suppression, which removes unwanted background noise from audio signals. Expressive states if you use their IDF, it automatically installs itself, but I found under VS Code Platform I/O, I have to manually flash it to the ESP32, and have included at the top of the main CPP file simple instructions for the steps I used to make it happen. The good news is it's generally a one-time thing that you do once, and as long as you don't do an erase flash in Platform I/O, it will be there from one project change to the next. Again, this filter and its companion pieces could be a whole nother video, but totally off topic from what I want to cover here, but kept it because of its value as an SSB filter, and I wanted to show the code steps needed to use it in a real-world project. thinking those interested in voice-activated projects might find the setup part helpful. And finally, to be clear, I've only used the noise suppression part, so have nothing to offer about the command configuration side of it. But based on expressive documentation, this component could allow you to control something like a thermostat with a simple set of predefined voice commands. The last filter setting found in the project is something called a Wiener filter. I suspect this is German and am likely clobbering the correct way to say it. So for those who know, forgive me. For CW work, this proved to be the best filter I've found to date, so much so I now seldom listen to CW without it. The general case of the Wiener filter is based on using an FFT for input, then manipulate the data in the frequency domain, and finally apply an inverse FFT to recover the filter audio. Sounds simple and fairly straightforward using expressive DSP FFT libraries, that is until you hit the IFFT step with a streaming signal. However, for CW work, I'm not interested in recovering the behavior of multiple frequencies, so at any given moment in time only need to recover the behavior of a single frequency. This point allowed me to sidestep the IFFT piece and come up with what I call a modified Wiener filter. Given the limited interest in CW filtering and decoding, plus what can be done with Copilot, I'm not going to waste time walking through the strategy used. But for those who have a need for this type of filter, feel free to examine the code and to exploit it in any fashion that works for your project. We'll close the video with me not talking so you can better hear the filtered modes in actions.
An MG. Oh, I just turned the amplifier on, and I hate it because I hate fan noise. You guys, an MG. Oh, I just turned the amplifier on, and I hate it because I hate fan noise. You guys, how do you tolerate fan noise on these amplifiers? How do you tolerate fan noise on these amplifiers? Well, I don't have that problem with my amplifier. It's actually pretty quiet there, going. Well, I don't have that problem with my amplifier. It's actually pretty quiet there. Go ahead. Yeah, I used to have a SB230, and it was convection cooled, and I missed that because you didn't have to try to listen over this fan. Yeah, I used to have a SB230, and it was convection cooled, and I missed that because you didn't have to try to listen over this fan. That this is an old SB1000 amp that I rebuilt, and I tried to quiet it down and put a better muffin fan in it, but I don't know, I just can't stand it. I got rid of my big Henry 3KA because it was like a turbocharger going off over here at the floor.
I'm not hearing that bad, though. You sound just fine.
Thanks for watching and hope you find something useful in this project.